All right, so now let's continue talking about the exponential mapping. So let me just sort of set this up in the following way. So let's consider a coordinate chart. Right, and then what happens is that with respect to this coordinate chart, your curve has components x1 to xn, right? And you can think of essentially that this sort of vector field, right, the velocity vector field associated with the curve, right, is identified with a, let's see, x1 dot all the way up to xn dot. Okay, so and then we're going to define the exponential mapping. It's like in terms of the geodesic equation, right? The defining equation for geodesic is that sort of the second derivative of the curve vanishes. So the acceleration vector field vanishes, and then in local coordinates, this looks like following. Okay. So the second derivative of k plus the sum over the Christoffel symbols equals to 0, and then this is for k equals to 1 to n. So you get a system of n second order differential equations, which in general nonlinear, right? Okay. But okay, so the reason why I say this is because the way to sort of think about this is that the defining equation for the geodesic, at least in local coordinates, is a second order system of nonlinear differential equations. And so it's possible for you to set up an initial value problem associated with that, where you specify the initial positions and the initial velocities, right? So that's going to naturally lead to this idea of the exponential mapping. Okay, so the point is that, all right, so for every sort of vector in the tangent space to the manifold, right, there exists an interval, let's say I about 0, okay, and a unique geodesic gamma t, which depends on x and the vector, right, which is a map from I to the manifold, such that gamma of 0 is equal to x, and gamma dot of 0 is equal to the vector. Okay, so what am I really doing, and what is it related to this sort of discussion we had in local coordinates? So one basically saying that is, if I specify a tangent vector by specifying the base point and the sort of the vector direction, right, then there is some sort of curve, it's like, which is locally defined to some open interval, it's like about 0. You have a parametrized curve with the property that, you know, it's like the initial position is x and the initial velocity is c, and in addition to that, it is a geodesic. Okay, so that's exactly the setting we have here, right? You should think of this then, this as defining for you an initial value problem for this system of second order nonlinear differential equations, where you specified the initial position x1 to xn, and the initial velocity is x1 dot to xn dot, right? And as you know, that's sort of enough for you to, that's enough initial data for you to specify a unique solution to this second order system, or the system of second order nonlinear differential equations. Okay, so that's sort of why we set it up this way. Okay, so there are other properties of this curve. Moreover, right, we have the homogeneity property. That if you sort of rescale the vector, okay, so if you rescale the initial velocity, that is related to rescaling the time. Okay, so this is gamma of a times t. So this is sort of like being first order homogeneous. It's like in that variable. Okay, all right. Anyway, so this mapping, the mapping, I'm going to define what is called the exponential at x, right? It's a map from the tangent vectors at x. It's like to the manifold, right? And it's obtained by mapping a vector to the exponential at x of cos c, and then this is defined to be gamma at time 1 of this curve. All right, so what am I doing here, right? So as I said, it's like the initial conditions together with the defining equation for a geodesic gives you a initial value problem, and the initial value problem, it's like defines what is known as a flow map, which is a map from the initial data to the solution at any particular time. So you're going to evaluate that flow map at time 1, and this is then going to give you a map from initial data space to the value of the geodesic curve at time 1. And this is what is called the exponential map. Okay. Okay. All right. And then if it turns out that you know, the domain of definition of this is the whole of the tangent space for all x, then the manifold is called geodesically complete. Okay, so all right, let me just erase this. Okay, so if the domain of this exponential map is all of txm, right, for all x in M, then we say the manifold M is geodesically complete. Okay, so it has to be endowed with a particular affine connection. Okay, all right. So all right. Then the point is that this is also going to give you something like a coordinate chart, if you will, right? So okay, so it can be shown that sort of the exponential map, right, defines a diffeomorphism of a neighborhood let's say u hat of the origin 0x, right, which is in the tangent space at x to the manifold M onto a neighborhood U of x in M. Okay, that's perhaps not so surprising, right? So it's easy, obviously, to convince yourself that if you have the 0 vector, that the geodesic associated with that is sort of just the trivial curve, right, which starts at x and sort of stays at x for all time. So it maps the 0 vector. So the exponential map maps the 0 vector. It's like the exponential map at x maps the 0 vector at x to x, basically, right? And so if you have something which is in the neighborhood of the 0 vector, it will map to a neighborhood, it's like of x, right? So that's basically where all that's coming from. Okay. All right. So, okay. So if, moreover, U hat is star-shaped, and what it means for it to be star-shaped is that so if some vector is in U hat, then t times that vector is also in U hat for all t, which is an interval from 0 to 1. Okay? So another way to sort of think about this is that if you have some sort of domain, it's like, and you have the 0, so star-shaped usually respect to a distinguished point. If you have something here that if you have any point here, it's like which is in the domain, right, then anything in that line segment joining that point to the origin is also in that domain. Okay, so that's what's meant by U hat being star-shaped. Okay. Okay, so the reason, of course, why you want the star-shaped property is because, as you might expect, it's related to something having to do with the homogeneity property, right? Okay. Anyway, so then U is called a normal neighborhood. Fix. Okay. And then you can sort of, so far we've defined this exponential. It's like with a base point, you can think of it as being extended to the full tangent bundle, right? So we can define just the exponential, which is a map from Tm to M, right, in the obvious way, where you take a vector and you map it to the exponential at x of this. Okay, where of course x is the foot of that vector. Okay, and then you can check that x is differentiable, and as before, that if you take the exponential applied to the 0 vector, you get x for all base points, foots. It's like x in the manifold. And the other thing is that if you take d of this exponential in this direction, you get just that. Again, with the canonical identification, right? That the tangent space all right, so because M itself is not a vector space, right, but the tangent space at a point to M is a vector space, so you can look at a tangent space to that thing and identify it with that vector space, okay? All right, so of course, if you remember, this is one of the defining properties, if you will, of the retraction. So we're going to observe that this exponential is going to induce a retraction, right? So let me state the proposition. Right, so we'll let M be a manifold with an affine connection. Nabla. Okay. And the exponential map induced by that connection, again, it's important to remember that the exponential map depends on the choice of the retraction, right? So the exponential map on M, right, induced by Nabla is a retraction, and we call this the exponential retraction. Okay, all right. So the problem, of course, it's like with the exponential mapping is that it's difficult to compute in general enclosed form, right? So the exponential mapping is difficult to compute in closed form. And we saw that because the defining sort of properties of the exponential mapping are in terms of the geodesic equations, which are the system of second-order nonlinear differential equations, which again are difficult, where the coefficients, it's like in the differential equation, involve the Christoffel symbols, right? So that's again a hard thing to do. So that's of course the reason why it's like earlier on it's like we introduced the idea of retractions. And of course, we saw that the exponential map is an example of a retraction, and we're going to have something it's like which approximates that in some appropriate sense, but which still retains all the properties we need. It's like an R-proof convergence, right? So we use instead sort of retractions, which are easier to compute. But retain the essential properties necessary for proving convergence. Of optimization algorithms on manifolds. Okay, all right. So that's one thing, and then the other thing is that the exponential mapping also gives you coordinate charts. Okay, and the way you sort of see that is that if you have the exponential map, it's a map from tangent spaces to M, right? And in particular, the exponential at a particular point is the map from tangent space at X. It's like to M. It's like to M. Okay, and so this has the structure of a vector space. In order to extract coordinates out, that you have to choose a basis, right? So to extract coordinates, right, we pick a basis. And if you have a coordinate chart, it's like on M, there's a natural choice of basis. It's like which comes from, if you will, well, actually, no, right? We're trying to actually construct the basis. Okay, so we pick a basis, right, for TXM. All right, so then a chart can be defined. Okay, so before I do that, so you extract coordinates, you pick a basis for this, and let U be a normal neighborhood of Y, of X. Then we can define a chart. That maps X. Well, okay, I've chosen X to be the base point. Let's map Y in U, right, to the components of the vector C in TXM, satisfying sort of the obvious relationship, which is that the exponential at X of C is Y. Okay, so in essence, it's like what I'm saying is that I'm looking at the inverse of the sort of the exponential X map from M to this, and I have identified this with Rn by picking a basis for TXM, right? And then this is what is called normal coordinates, right? Called sort of normal coordinates, sometimes geodesic normal coordinates. Okay, and then the other remark, if you will, it sort of ties in. It's like this thing we had said, where straight lines can be characterized in two different ways, right? In Rn, it's like one of which are that they are zero acceleration curves, and then the other of which is that they are length minimizing curves. Okay, so so it turns out that these two things are related. So, okay, so if M is a Riemannian manifold, right, a curve with minimal length, which you can measure, of course, using the Riemannian metric between 2 points of M, right, is always a monotone reparametrization of a geodesic relative to the Riemannian connection. Okay, so what is that basically saying? So that's saying that if you have a geodesic, it's like in the sense of connections where you've chosen the Riemannian or the Levi-Civita connection associated with the Riemannian manifold, then that curve, right, is going to be length minimizing on the one hand, and then conversely, you know, it's like any curve which is, you know, it's like length minimizing, right, is going to be a reparametrization, it's like of this sort of geodesic in the sense of the Riemannian connection. Okay, so these curves with minimal lengths are called minimizing geodesics, right? these curves are called minimizing geodesics. So the upshot, if you will, is that if you have a Riemannian manifold and you endow it with the Riemannian connection, right, then up to this sort of issue of reparametrization, you know, it's the notion of geodesics in the sense of, you know, it's like zero acceleration, it's like defined in terms of the Riemannian connection, is equivalent to the notion of curves which are length minimizing. Okay? All right, so let me just sort of also finish up. It's like by saying something about sort of this parallel translation issue. Okay? All right, so this is sort of this parallel translation. Okay, so you let M be a manifold with an affine connection. Nabla, right? The vector field sort of C on the curve gamma, satisfying the property that this derivative of C along that curve is called parallel. Okay. So, given A in the reals, in the domain of gamma, right? And C gamma A, right? In the tangent space at gamma A of the manifold, right? There's a unique parallel vector field. C, right, on gamma such that C at A is equal to C gamma at A. Okay. So, so the operator, let's call this P. It's like from B, it's like from A, it's like in gamma, sends C at A to C at B. Okay, sending this is called parallel translation. Sometimes called parallel transport along gamma. So what that means, right, by definition, is that if you take this derivative, so that means that take the derivative P B to A gamma CA, right, that's equal to 0. So if M is a Riemannian manifold, nabla is the Riemannian connection. transport. Or translation induced by nabla, right, is an isometry. What do we mean by that? Let me sort of draw a picture for you. What I mean by this is the following. So say you have a curve, right, gamma of t, and you have two sort of vectors. All right, and you parallel transport them. Or you parallel translate them, right? Then, with the inner product given by the Riemannian metric, right? This inner product between those two vectors and the parallel transported version of those two vectors is the same. Okay, so this is what I mean by it being an isometry. Okay, so all right. So as you might expect, the same way that the exponential map is an example of a retraction, this notion of parallel translation is going to be an example of a more general notion. And the reason, again, to consider a more general notion is because, like with the exponential map, it's difficult to compute exponential maps, so you want to have something easy to compute, like this more general retraction. The same is true here, that in general, the parallel translation is difficult to compute, and you want to have some sort of more general object which is easier to compute. Okay, so the parallel translation is an instance of the more general notion of vector transport and so sort of these sort of more general notions are used to construct sort of computationally practical optimization algorithms. On manifolds. Okay. All right. Okay. So let me just stop here for now, and then the next thing we'll talk about is how to talk about Hessians. It's like because of course that's one of the things we want to do if we want to try to generalize the notion of Newton's method. It's like to manifolds is to talk about Hessians or scalar value functions. So let me just stop here for now.